Today we are going to do section, what is this, 2.4. So first let's take a look at the textbook. This is the page that's already scanned from, let me move that a little closer. All right, that should be good enough. Why does it look different? Anyway, so that's that. Okay, next, this is page, what is that? Okay, this is 76, 77. It doesn't seem very clear. Okay, and then a little bit to the top and bottom. All right. Finally, 78 and 79 is a fairly short chapter, section. Let's see, I hope you can see that okay. All right, and then a little closer on top. And a little bit closer on the bottom. Okay, that should do it. So let's look at page 76, where we talk about surfaces. The surfaces right now we're talking about are the ones that we're familiar with from basic calculus. They can be represented by several ways, such as a function f of x1, 2, and 3, or another we used to call it x, y, z. Okay, if it's such a function equal to 0, that will represent a surface. Or it can also, of course, be equal to such a function as x3 equals f x1, x2. Now, specifically in this section, we're going to talk about the parametric representation of a surface, which then you have a vector x, y, and z. In this case, we call it x1, x2, and x3, each one represented by u and v. So then we have, we write it in the vector form, then it's just one line, okay, where we have the vector x is the vector function uv, and this just means that. This is a compact way of saying this, okay, x1, x2, and x3. And we will call this thing equation 1, the parametric representation of x into vector x with two variables to represent a surface. So next, having said that, the next part is a bunch of examples from basic calculus, such as example A talks about the sphere. Okay, next page, example B, the plane, and then example C, the cylinder, the round one, okay, and example D, the cone, and even example E, the torus, that is the donut. Okay, all those have been covered fairly extensively in basic calculus. This is just a reminder of what we learned in the past. So please read those parts yourself, so that we can move on to the next section of proving new theorems. At the bottom of page 76, notice that from now on, our functions that we're thinking about, we will assume they are C1, that is the first derivatives, first partial derivatives are all continuous, so we don't have to deal with any weird problems. And so let's now go to page 77, where we consider theorem 4. Theorem 4 states that if you have the partial derivatives of all three, the vector, the function we're talking about, that is x in terms of u and v, all three components, okay? If equation, we call it equation 1. So if that vector function represents a point, equation 1 represents a point if and only if the partial derivative with respect to u and v are identically 0. Then it must be representing a point. The book didn't write this out, but I just quickly wrote it out. It doesn't take much, right? For example, if you have the partial derivatives equal to 0, let's say, first let's consider the fact that partial u is identically 0. That means that x had better be a function of v. But then partial v is also 0, means x is stuck with being a constant. See, a quick proof of why when the partial derivatives are all 0, then the whole thing doesn't go anywhere. Okay, it's just stuck at a constant point. All right. So next we consider theorem 5. But before that, we read this part where equation 1, that is x of t, is represented by u and v, the parametric representation of x of t. It may represent a curve. Now, when would it represent a curve? Now, here's an example when it might represent a curve. This thing is as given here. Okay, is the intersection of some plane and the cylinder. Now, please verify that yourself. That is a quick, easy verification, I believe. And then, so next, if it represents some curve, then, but if it does represent a curve, then the curve is always represented by one variable, t, right? And which means t has to be a function of u and v. And therefore, we can calculate that, so we can plug it in, okay? That is, we plug t as a function of u and v where t used to be, and then we can check out certain things. So once we put it, here's on the page, 77. So if x equal to, is a function of u and v, t of u and v, which means x is now a function of u and v, even though it's a curve. So then we can take the partial derivatives, then xu is xtu, and so on by the chain rule. And as a result, when you cross those two things, you end up with just some x cross x prime crossing itself. And anything cross itself is 0. And therefore, for something to be a curve, the cross product had better be 0. Okay, so then we will show in the opposite way that this condition also implies that the equation is represent a curve, and that is theorem 5. Okay, so let's read theorem 5, where it says that we have x of u cross xv is identically 0. And remember what x is. X is the component function, okay, of three components, x1, x2, x3, and each one of them dependent on u and v. So that's what equation 1 is, okay. Throughout this section, bear this thing in mind, where x is, this is in the previous page, where x is x of u and v, and x1, x2, and x3 all look like that. Okay, everybody depends on u and v because we're talking about the parametric function. So with that in mind, let's consider xu cross xv identically equal to 0 in some neighborhood of u and v, u0, v0, the point that we picked. So then, and also there's the condition that xu, which is a vector, okay, that is the partial derivative with respect to u for all three components, the vector is not 0, or the partial v1 isn't 0. Either one is fine. If this is the case, then equation 1, that is the x that we're talking about, the vector, represents a curve where u and v in a sufficiently small neighborhood of u0, v0. So this thing will be a curve at least in a small point. All right. So now, having said that, let's see the proof. Now, hypothesis 2, being that the two vectors are not 0, then at least some component of either one is not 0. So let's assume that partial x2, partial v is not 0. We can assume some other thing that would be fine too. But we'll pick this one just, well, basically at random. Okay, so by hypothesis 1, then we can calculate something, the two Jacobians is going to be identically 0. Now I have it written down here. Now, the Jacobians are 0 because of hypothesis 1. And you might wonder, why would that be? Now, I have it written down. Hypothesis 1 is this thing, right? Partial u and the partial v cross product is 0, which if you write it out, you get the ijk business, where each one of these, if it equals the ijk and it's identically 0, means each component becomes 0. Now, one of them, the x1, the Jacobian of x1, x2 against uv is the component for k. So that has to be 0. The other one, whereas x2, x3 against uv is 0, that is, what is that? The I component. Okay, so that's why these two Jacobians are 0, is because of hypothesis 1 if you write it out. Okay, it's not obvious if you don't bother to write it out. So now that we know the Jacobian are 0, we're going to pull out some big guns from the past. Okay, and specifically, we're going to pull out theorem 15. Let's look at theorem 15 from back on page 58. Now, theorem 15 says, what was theorem 15 again? It was about functional dependence. That is, if you have two functions and somehow some kind of Jacobian is 0, but some partial derivative is not 0, then the one function is somehow can be pulled out of the represented with another. That is, there's a third function that is with only one variable, such that you can stuff one into the big function and the other one comes out. Okay, so that is what we're going to use. As a result of that, we have this situation. So we can crank out two functions. And first one, x1, is some kind of a thing of x2, plug one into the other because of some Jacobian satisfying, and because of something isn't 0. See, there are two requirements for theorem 15. The Jacobian has to be 0, and some partial derivative is not 0. But anyway, once you checked out all the details, then you realize that this does work. So then x1 is some kind of a representation. You have big function f and g such that x1 is something represented by x2, and so is x3. So they're both functions of the two. So x3 is represented by x2, and x2 come from what is that? x1 by x2, and then x3 by x2. So please check all the details and make sure everything comes out like it's supposed to. Okay, and then but we will move on. Okay, but take your time in confirming that everything about theorem 15 is satisfied. So once you've done that, then let's check this. Then this means, what does this mean? It means that the projection on the x1, x2 plane is x1 equal to fx2. In other words, it is a line. The projection is a line. Okay, that's what those two equations mean. And then x3 is a different line for the two projections. So and then the book then says equation 1 therefore represents a curve. Now that in itself doesn't show that it represents a curve yet, because you can totally have a surface. Okay, like let's pretend this is a surface, right? That if you were to project downward on the bottom plane, it would be a line. And so is projecting sideways. So it has two orthogonal directions where the projections are just a line, but that doesn't mean that this thing is a line. Okay, there's still a third surface to think of. Your book hasn't bothered to say that, but what happens is that right now we have proof that there are two projections are lines. Well, what about the third projection? The third projection is also a line. Why? Because we can go through the same process just with different variables. In other words, we can, for example, say that x1 is a representation of x3, and x2 is also a representation of x3, which is similar to what we did before, which is we did x1 represent of x2 and x2 represent x3 or something like that. But anyway, we can just shift but there was no reason to do that. Okay, we could have chosen any variable, which means we could have shifted the axis and then proven a third one that also has a projection of a line. So if something has three projections in the three orthogonal directions, all being lines, then this thing had better be a line. Okay, then that is or a curve is what I mean. A line implies a straight line. I just mean any old line. In other words, a curve. So that is the proof of this theorem. And of course, being that we chose some random component partial derivative as not 0, okay, we could easily chosen anything else, and that would work too. I mean, any other partial derivative. And right now we chose x2 and then chose v. It could be x1 and u, or x3 and v, whatever, right? So that's as a result, this theorem can be is established. And what are we doing? We are proving that the vector function, the parametric vector function, represents a curve if the condition that xu cross xv equal to 0, and xu or xv isn't 0. Okay, so that is theorem 5. And so next, let's go to the following page 78, and let's look at theorem 6. Theorem 6 says that, and remember, we have earlier mentioned that we assume everything is in C1. Okay, all the component functions are in C1. This is on bottom page 76. So remembering that, so everything is smooth. Okay, we don't have to worry about weird stuff. Now, if everything is C1, then we can take partial derivatives, of course. And then if the cross product of partial u, x partial u cross partial x partial v is not identically 0, that means equation 1, it has to represent a surface. Now remember in theorem 5, we said if it is identically 0 plus some other minor condition, then this thing is a curve. So if it's not 0, then this thing is a surface. And then we are going to prove that. Okay. Now to prove theorem 6 on page 78, we need to look at that cross product, okay, which is not supposed to be 0. We wrote it out in the previous proof. So let's go back and look at it. Well, first, let me find it. Okay, the cross product means that all these things, which is basically the 3 Jacobians, are not 0. Okay, so then we'll assume that this Jacobian is not 0. Well, no reason. We got to pick something. So let's say that's the one that isn't 0, being that the cross product isn't 0. So one of them had better not be 0. Now, if this one isn't 0, then we'll call that equation 1. Okay, so we're assuming that this Jacobian, which in this case is written like that, which is fine. And so we'll assume that this particular Jacobian is not 0, which then we will then show that somehow, in this case, we have the Jacobians again is x1 and x2. We will be able to show that the x3 is somehow a function of x1, x2. Because if that is the case, then that is a surface, okay, if it's defined around some neighborhood. And so the next step we're going to do is pull out theorem 16 on the previous chapter, which is on page 69. Okay, and this thing which says that if you have two big as the simultaneous equations, right? When you have two big functions, big F and big G, involving u, v, x, y, and when they're both 0 around some neighborhood, and then some Jacobian isn't 0, then we can do this. Specifically, we can yank u and v out, okay, and come up with some small f and small g, such as u and v is a function of the original x and y's. So, having said that, then let's do this. So I have it written down here. We have, let's see. First we have I lost my page. Give me a second here. Why do I thought I had it on the, oh yeah, I need to turn the page. All right, so to apply this theorem, I wrote it down exactly like the theorem says, okay? Our equation is, what is the equation that we do have? Okay, this is first, for the definition, by definition, the x1 is x1 of u and v, right? x2 is x2 of u and v. And we also have x3, but we'll ignore x3 for a second. And we'll just focus on x1 and x2. Applying theorem 16, I wrote down the big F exactly like theorem 16, so that we can see it better. And then calculate this Jacobian, which theorem 16 requires. And you notice that by the time you calculate the Jacobian very quickly, okay, you notice that's exactly the equation 1, or whatever this thing is that we were looking at earlier, okay, the Jacobian we were looking at earlier, which is not 0. So this thing is not 0, which is just about the only requirement for theorem 16. So once that's done, we apply theorem 16, and we know that u can be we can pull u out of this thing, okay, as a function of x1 and x2, and same as v by applying theorem 16. And now that we have this, if u is a function of x1, x2, and so is v, we're going to plug u and v into x3, because x3 is also the components. The third component is a function of u and v right now. If we plug u and v in terms of x1, x2 inside, so then there's no more u and v, and only have x1, x2 as some kind of function, okay, and some neighborhood, and therefore this is a surface. Because anything that is a third variable in terms of is a function of two other variables, that thing is a surface, okay? And that is how we finish the proof. Now, of course, in this case, we assume that one of the Jacobians isn't 0. If that's not the case, it's actually a different Jacobian that's 0. That's not 0. I'm talking about this one. If it was a different one, the proof will go exactly the same way. So it doesn't really matter which one we pick, which one we pick to do the proof. It could be, like right now we did x1 and x2. It could be x2, x3, or whatever. Okay, and so then, let's move on to the next part. Now the next part is we consider that when this product is not 0, as we have just used as a premise in Theorem 6, then it actually end up, the cross product is actually the normal vector to the surface. Well, Theorem 6 says it's actually a surface, and this statement says that, which we'll prove later, that if it is not 0, then not only is this x a surface, but that this cross product is the normal to the surface. Okay, but we'll figure that out later. Okay, and but for now, we'll think about something else interesting. That is, if the cross product xu and x cross xv is not 0, okay, then the point where we're talking about is called regular. Whereas at a different point where the cross product is 0, it will be called singular. As an example, in the previous example D that I asked you to read, which represent the cone, you will notice quickly that the vertex of the cone is singular. Okay, the partial derivatives goes to 0, whereas all other points are regular. Now, you might think, well, does that mean singular points are all weird points, like the tip of the cone? Not necessarily. Sometimes points will end up being singular even though there's nothing singular about them. For example, in example A, the North Pole and the South Pole will end up being 0 if you take the partial derivatives of them. But there's nothing special about them. The North Pole and South Pole look just like any other part of the sphere, right? So that's just the result of the parameterization, because if you change the parameterization such that something else is now considered the North Pole, and like say sideways, okay, and then in that case, then those new North Pole and South Poles will have the partial derivatives equaling 0. So the singular doesn't necessarily mean that something odd is going on, but regular definitely means everything is going great. Okay, there's nothing odd going on, like a sharp point or anything like that. So having said that, that is the end of this this section. Let's please do homework on page 78. Problems 1, 2, 3, and 7, 8, 9 is a short. This section doesn't have as many homework, so please do that. And when you come back, I want to talk about them. So problem 1, we have to spin around some ellipse. Okay, to do that, we have to. Well, first we have to look at what the ellipse is. The ellipse is this equation, which the parametric representation is that one. Okay, no, I think I wrote that down. That should be B. All right, but anyway, yeah, y is b and x is a, and if you plug those things in here, then you'll get the equation to come out. So we're gonna spin this thing, and there is not much to explain here. Okay, here's the graph I drew. You got to remember that eventually this thing, as it spins out, then this line here is still, that is across is a cosine t. Okay, but this, as it spins out, this diagonal line is still a cosine t. So then the x and y value is correspondingly a cosine t, then you times cosine u, and the other one is sine u to get the x and y value. With u and t varying the proper amount, and whereas the height z still stays as sine t, the b sine t, which is the other variable for the ellipse. And once you do that, that is about it. That's the parametric representation. And then then for problem 2, you realize that in general, if you have some curve, we'll put the curve on the YZ plane and spin it around the Z axis. So then if you have a curve where Y is f of t and C is g of t, then you just stick then the x coordinate, which is x1 in our homework, okay? x1, x2, x3. So the x coordinate is just let's see which one, the y string length right here, okay, times cosine u, and the other one is f of t times sine of u, and then everything will come out the same way. That is the parametric representation of any kind of curve that you want to spin around something. Okay, so that is problem 2. And then problem 3, we have, problem 3 says we have some plane, and the plane has some interesting description. The first part says something about the plane has to be, the position is determined by its algebraic distance to the x3 axis and its algebraic distance, well, whatever. What does that mean? And what it's saying is that u is the algebraic distance to the something. Okay, what is that? And x1 and x2. So u is the distance. Is that what it said? I hope so. U and V respectively represents the algebraic distance. Yeah, so U is the distance to the x1, x2 plane, the xy plane. So then the U equals to the square root of sum of squares. And eventually, and if you plug this in, okay, the x2 is actually 2x1, then you end up with the square root of 5x1. And then in the meantime, V is just x3 because it says something about V is, what was V again? V is the algebraic, the first one is algebraic to the x3 axis. So it's the distance, and the other one is the x1, x2 plane, sorry. So this is that's the distance to the z axis, okay? Anything to the z axis, it better be this. And then this is just to the plane, which is just x3. So then we have this information out. So then x1 is equal to, from this equation, u over square root of 5. x2 is then, from this equation, 2u over square root of 5. And x3 is just v. Now so that's the parametric description of this thing. Now I can prove that that is the case, being that we don't have the answer at the back of the book, but I do have a proof, okay? Now my proof here, I plotted both of these things. First, this is the description of the plane in red, and then here's the parametric, the representation that I calculated, and now I type it in here, and look at that. The red and the blue coincide, okay, superimpose, whatever you want to call that. They're exactly the same. So if you plot this into the Desmos calculator, you will get the same thing. See, looks pretty good, doesn't it? Yeah, and just think back when the book was written, they couldn't do anything like this to be sure that this actually works out. So that is that's that. That's problem 3. Next. Problem 7, we have 2 equations with a bunch of stuff being squared. And because it's being squared, I just automatically write down the u cosine v, u sine v trick, okay, the standard trick for this type of thing. And if you do that, then you realize then very quickly that you can just say x1 equal to u plus 1, and then and call it done. Okay, and so that's that all works out. And then the next one is we have to calculate some singular point. So I did that. So here's xu, xv, the cross product. And then what happens when it's 0, then all 3 things has to be 0, which means the u has to be 0. Okay, if u is 0, v can be anything really. And then the whole thing will be, the singular point for this thing will be at 1, 0, 0. And that should be it. So next we are, But anyway, this thing, I plotted it out, but I can't find it right now. But it is, if you plot it out, I believe it's some kind of a cone. Why don't I have it? I thought I had. I don't care. It's not that exciting. It's a cone, okay? And the singular point is the tip of that cone. I think it's a double cone that goes up, and then there's a tip, and then it goes down. Anyway, let's move on, okay? The problem number 8, we have some surface, okay, and we're supposed to prove that a whole bunch of complicated looking determinants equal to 0. So I just did one of them, and by writing stuff out, what are we doing here? That is, if we'll take the partial derivatives of various things with respect to u and v and uu and write it all in and take a good long look at it and realize that the determinant is the sum and then multiple of various other rows, and which is why the determinant is has to be equal to 0. Yeah, something like that. Okay, so this break into two determinants. If you split up the plus sign, and then they're both 0. So therefore, the determinant is 0. And the other versions where it says x, I don't know, uv or whatever, should be similar. And yeah, and I'm not doing it. So that's that. And next, let's look at problem 9, where we have this odd-looking parametric representation of something. And I was looking at it, and I was thinking, that is basically odd looking on purpose, okay, just to mess with you. So what we're gonna do is I wrote down these different components, and I was staring at it, and I thought if we multiply it by some number, then it will turn and get rid of all the weird looking parts. Okay, so to stare at it, to get rid of EU and minus EU, I decided to choose A1 equal to 2, A2 also equal to 2, and then A3 will be equal to minus 1. And with that, I was able to cancel out every last thing, okay? And so this whole thing then equals to K, which is 13. All right, so the plane then, I write down A1, A2, and A3. The plane that this complicated thing represents actually just this thing at all. This is just a simple plane. The reason this is possible is because parametric equations are not unique. Okay, there's more than one way to skin the cat. In fact, there's endless ways of skinning cats. So then, at least this cat. So then that's why the plane, that big complicated looking, odd looking thing, is actually just a simple plane, which I have it drawn right here on the Desmos calculator. And as you can see, the red one is the original representation, okay? And then the blue one is the one I cranked out. And you notice they superimpose. They are exactly the same, except that the red one doesn't spread to the whole blue screen because the red one has a sign in there. So the value of v in those parametric representation are limited, and that's what happens if you put the sign in there, then you might not get the sign value only goes from -1 to 1, so it'll never get past a certain point. But you can still extend it, of course. In the other representation, there's no limit, and therefore you know that this thing is a plane just like the other thing. And with that, that should be the end of this section.